Okay, let's talk about quantum computing. I want you to imagine a computer that could solve problems in just minutes, that would take our best supercomputers today billions of years to crack. That's the promise here. It's a field built on rules that, honestly, seem to defy all common sense. But it's a field that could absolutely change our world.
You know, the famous physicist Richard Feynman once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." And he was so right. This perfectly captures the sheer strangeness of the quantum world. We're talking about a realm where particles can be in multiple places at once and are somehow mysteriously linked across huge distances.
So that begs a pretty big question, right? If even the experts are stumped, how on earth are we supposed to build computers with this stuff? Well, that's exactly what we're going to find out, because today, we're not just observing quantum mechanics anymore, we're actively controlling it. We're going to see how all this weirdness becomes an incredibly powerful tool.
All right, so here's our game plan. First, we'll go from the weirdness to reality. Then we'll hit the two big principles you need to know, superposition and entanglement. After that, we'll look at how scientists are actually building these things, these artificial atoms. And finally, we'll put it all together to see the foundation of it all. Okay, first up, let's start with the absolute heart of any computer, the bit. Because this is where you'll see the first huge difference between the computers we use every day and this strange new world of quantum computing.
So your phone, your laptop, they all run on classical bits. The easiest way to think about them is like a simple light switch. They're either on or they're off, a 1 or a 0. It's a definite, straightforward state. But a quantum bit, or qubit, is a whole different ballgame. Take the spin of an electron, for example. When we measure it, sure, it's either spin up or spin down. But the real magic is what's happening before we look.
So what is it that makes a qubit so special? Well, this is where we leave the world of simple on or off switches way behind, and we enter the world of superposition.
This is it, superposition. It's not that the electron is somewhere in between up and down. No, it is, in a very real sense, both up and down at the exact same time. This is probably the first mind-bending idea we really need to wrap our heads around.
But here's the catch. This crazy both up and down state only exists before you look at it. The very instant you measure the electron's spin, it's forced to choose, and it collapses into just one definite state, either up or down. But, and this is so important, while it's in that superposition, it holds way more information than a simple 0 or 1 ever could.
So how do we even begin to visualize this? Well, scientists use something called the Bloch Sphere. Think of it like a globe, but for a qubit. The North Pole is pure up. Let's say that's our 1. The South Pole is pure down, our 0. But every other single point on the entire surface of that globe represents a unique combination, a different superposition state. It gives you an idea of just how much information is packed in there.
Okay, so that's one qubit, but things get even stranger and a whole lot more powerful when we link two of them together. This brings us to entanglement.
So, if we have two separate independent qubits, their outcomes are totally random. Measuring the first one tells you absolutely nothing about what the second one's going to be. All four possible combinations, 0, 0, 0, 1, 1, 0, and 1, 1, have an equal 25% chance of happening.
But with entanglement, the game completely changes. Look at this. The chances of getting a mixed state, like 0, 1 or 1, 0, just drop to 0. Impossible. Their fates are now linked. If you measure the first atom and it's a 0, you know, instantly, without even having to measure it, that the second one is also a 0. The same goes if you get a 1.
This is what Einstein famously called spooky action at a distance, and this link holds true even if these two atoms are on opposite sides of the universe. It's an instant connection. And this powerful correlation is a key resource for quantum computation.
So this all sounds great in theory, but how do we actually create and control these bizarre states in the real world? It's not magic, but it is some incredibly precise engineering.
Well, one way is to use actual atoms. Scientists can isolate an atom and then target two of its specific energy levels to act as our 0 and 1. Then, a precisely timed laser pulse, called a pi pulse, can flip the atom from state 0 all the way to state 1. Think of it like a 180-degree turn. So how do you create that perfect 50-50 superposition? You just zap it with the laser for half the time. It's called a pi/2 pulse, and it's like a 90-degree turn.
But most of the quantum computers you see in pictures, the ones that look like these crazy golden chandeliers, they use a different method. They actually build their qubits out of tiny, custom-made electrical circuits that are cooled to near absolute zero. And because they have distinct energy levels just like real atoms, we often call them artificial atoms.
And what's really amazing is the principle is exactly the same. You target two energy levels, you use a pi pulse, that 180-degree flip, to change the state, and you use a pi over 2 pulse to create a superposition. The only difference is, instead of a laser, we're using very precisely controlled radio waves.
And how do they create that spooky entangled link? Well, it's surprisingly straightforward. You just build the artificial atoms physically close to each other on the computer chip. That's it. They naturally start to interact and influence one another, and that allows engineers to generate entanglement.
Okay, so we've got superposition and we've got entanglement, and we know how to create them. So let's put it all together and see how this all builds up to this powerful new kind of computation.
When you boil it all down, quantum computing is really built on these two pillars. Superposition lets qubits exist in this rich combination of states, exploring multiple values all at once. And entanglement creates these incredibly powerful, intricate links between them.
And here's the real key takeaway. It doesn't matter if it's an atom, or a superconducting circuit, or even a photon of light. If you have a physical system where you can reliably control these two phenomena, superposition and entanglement, you have the foundation of a quantum computer.
By harnessing all this weirdness from the quantum world, we're not just making a faster version of the computers we already have. We are building a machine that operates on the fundamental principles of reality itself. And this unlocks an entirely new way of computing, which just leaves us to wonder, what revolutionary discoveries in medicine, in material science, in artificial intelligence are just around the corner, waiting to be unlocked by the power of the quantum realm?